We begin our discussion on probability and statistics by defining random variables. So a random variable is any variable whose value is subject to chance. For example, suppose I take a coin and I flip it. The outcome of that coin flip is subject to chance. It could be heads or tails, but I don't know in advance which of those outcomes it's going to be. To take a more physicsy example, suppose I choose a molecule in the room at random and I measure its speed. Well, that speed is going to be subject to chance. Different molecules are going to have different speeds. Therefore, I can't be sure ahead of time, without having chosen the molecule, what speed I'm going to get. What causes the variable to be a random variable? Or to put that another way, why is there chance? Well, there's a couple of different reasons why we could end up getting chance in any experiment that we do. One reason is that we could have a lack of information. Suppose you set up a projectile measurement and you want your projectile to land on some spot. You mark it with an X. Why might it not land exactly on the X? Well, there's a lot of things that go into that experiment. You need to know the launch angle that you are firing your projectile at. You need to know the velocity that it leaves at. You need to accurately measure the distance between your starting point and your X. There's a lot of different measurements, and all those measurements have some uncertainty to them. No measuring device we have is absolutely precise, so practically, there's always some lack of information. There's always some uncertainty with the values that go into our calculations that will prevent us from having an exactly correct result. There's always going to be some random fluctuations on it. Maybe I overshoot the projectile, maybe it runs too short. But it would be surprising if it landed exactly on the X every time. Now that's more of a practical matter. However, even if we didn't have those practical limitations of measurement accuracy, we would still run into the issue of quantum mechanics. So according to quantum mechanics, variables that we measure are fundamentally random. We have some uncertainty where even if I measure the position as accurately as possible of an electron, I take the best instrument we have, I measure its position, fundamentally I cannot know the velocity. The very act of measuring the position destroys whatever the velocity was and changes that into a random variable. This is known as the uncertainty principle, and to the best of our knowledge and to the best of any theoretician's knowledge out there in the world, that is something that is fundamental to the universe. It is a type of randomness that we cannot get around. In order to deal with random variables mathematically, it's helpful to classify them into different groups. One group is discrete random variables. These are variables that can take only a countable number of values. For example, if you flip a coin, you have two values. You have 1, heads, or 2, you could get tails. If you roll a dice, you have 1, 2, 3, 4, 5, 6 possible values, if you have a 6-headed dice. I can count the number of outcomes. Taking a more physicsy example, if I have, let's say, a hydrogen atom, and I want to count the number of energy states. Here's my hydrogen atom. If I measure the energy is a discrete random variable because I can count the energy states. I can say it's at minus 13.6 electron volts for the first state. For the second state, it's at minus 3.4 electron volts. If I go up to the nth state, it's at minus 13.6 electron volts divided by n squared, where n is just any integer. So I can count the integers. Therefore, I can count the different energy states of the hydrogen atom. These are all examples of discrete random variables. Another type of random variable we will consider is the continuous random variable. A continuous random variable is any variable that can take an infinite number of values within some range. So, for example, suppose I have a gas of molecules. And I choose one at random, and I measure that molecule's speed. Well, the speed of that molecule can be anything between 0 and the speed of light, which we denote by c. And it can be any value, not even a countable number of values. It can be any real number between 0 and 3.0 times 10 to the 8 meters per second. That would be a continuous random variable because it's all the numbers continuously from 0 to the speed of light. Similarly, if I'm measuring the distance between two galaxies, that distance is also a continuous random variable. It can take any positive real number. So continuous random variables can have an infinite number of possible values. Finally, we have mixed random variables. Mixed random variables are called such because these variables can take on both continuous and discrete values. So we can, for example, look at a proton and an electron. Now, usually we think of this as making a hydrogen atom, but if the electron has enough energy, it can go free. So we could have the energy levels of a hydrogen atom, minus 13.6 electron volts, minus 3.4 electron volts, many more energy levels in there. But if the electron has a positive energy, then it is no longer its energy is no longer quantized. It can take any positive value of energy. So since it can take any positive value of energy, the positive values would be continuous, all the way from 0 to infinite. The negative values of energy would be discrete, because I have a countable number of energy levels that the electron can be in. So this is an example of a mixed random variable, because it has both continuous values and discrete values. Now we want to discuss probability. So to take a simple example, suppose I tell you that I am thinking of some integer between 1 and 10, and I want you to guess its value. You're going to guess some value. What's the probability that you have the correct value? Well, the integer I am thinking of, as far as you're concerned, is a random variable. In this case, it's a discrete random variable because it's some integer between 1 and 10. Now, assuming there's no biased statistics here, so I'm not more likely to choose 3 than 5 or 6, etc., then the probability of getting the answer correct is just going to be 1 divided by the number of possible outcomes. In this case, since you have 10 possibilities, the probability will be 1 out of 10. By convention, we want our total probability to add up to 1. So in this example, where we have the probability of any individual outcome, I'll actually label that PI, is 1/10. I want it to be true that the total probability, so P1 plus P2 plus ... all the way up to P10, since I have 10 possibilities, I want my total probability to add up to 1. This is why I end up getting the probability of 1/10 if we're talking about picking an integer between 1 and 10. This condition, that my total probability adds up to 1, is known as normalization. Normalization. And if my probability distribution is normalized, we say that it adds up to 1. Suppose I tell you now, I'm thinking of a number between 1 and 10, and I want you to guess the number. What's the probability that you'd be correct? Well, had I said I'm thinking of an integer between 1 and 10, the probability would just be 1 out of 10. However, If I'm thinking of a real number between 1 and 10, your probability of getting that correct goes dramatically down. So we said before that the probability is just 1 over the number of outcomes. So if I have 10 possible guesses that I can make, the probability of being right is 1 out of 10. However, if I have a real number, if I'm thinking of a real number between 1 and 10, I have a lot more possibilities. There is an infinite number of real numbers between the values 1 and 10. I could choose 1, I could choose 10, I could choose pi, I could choose 5, I could choose 5.3279876. I could choose any of those numbers, and they would fall between 1 and 10. There is an uncountably infinite number of possible values I could choose between 1 and 10. So how do we deal with probability if we have a continuous distribution? If we have a continuous random variable that can take an infinite number of possibilities, how can I compute my probability? When dealing with a continuous random variable, we know that probability will not work, because to find the probability of guessing the correct answer, I take 1 divided by the number of possible outcomes. However, there's an infinite number of possible outcomes if we're talking about the probability of finding some number between 0 and 10. So how do I deal with that? Well, I might have an infinite number of possible outcomes for finding some number between 0 and 10. But I can still do a pretty good job if I give myself some range of values. So for example, suppose I am interested in finding the probability of guessing a number between 1 and 3. What's the probability that if I'm thinking of a real number between 0 and 10, what's the probability that that number lies between 1 and 3? Well, 1 and 3 spans a range of 2. And that range is 1/5 of the total range. So if my probability is uniformly distributed, so that any number is equally likely, then it must be true that since this is 1/5 of the total number of possibilities, there's a 1/5 probability that my value will lie between values 1 and 3. That the value that I choose for my random number between 0 and 10 falls between 1 and 3. So this leads us to a different type of probability, a different way of describing this. This leads us to something which we call probability density. Probability density. We have a few different types of probability here, so I'm going to try to denote these slightly differently. This is my uppercase p. You can tell because it has the little feet on it. My lowercase p is what we'll call probability density. Now, what do I mean by probability density? Here's what I mean by probability density. Probability density, which in general can be a function of x being my random variable, if I take that probability density p of x times some small range dx of values, that is the probability that the random variable lies between x and x plus dx. So if I were to have some probability density function, could be some weird complicated function, so I'll try to draw it, try to give it some weird complicated shape, and I look at some value of x, and then I look at some value of x plus dx, the probability that my value lies in this range between x and x plus dx is just that area. That is what we mean by the probability density. How are probability and probability density related? Well, if I go back to my definition of probability density, we said that p of x dx is the probability that my random variable will take on some value between x and x plus dx. Now, if I want to know the probability that my random variable falls in some range, what I can do is I can look at the range that I'm interested in. I can go from a to b, and I can integrate p of x dx from a to b. So equivalently, what I'm doing is that if I look at my probability density function as a graph, p of x is a function of x, and suppose I get some curve, and I want to know what's the probability of being in this range from a to b. Well, we can say the probability, just looking at this relationship here, I can get the probability of being between a and b just by taking an integral from a to b. So just by looking at this area under the curve, that area under the curve will give me the probability that my random variable has a value between a and b. We know our total probability must add up to 1 by convention. What does that mean for our probability density? Well, before, we looked at the probability that our random variable took on a value between a and b. If I want to get the total probability, I don't want to go from a to b, I want to go over the complete range of the probability density function, which we can encompass by saying this function goes from minus infinity to infinity. So let's integrate over the full range that of possible values this function can take. When I do that, it better be true, since I'm adding up all of the possibilities over all the possible range of values that my random variable can take, it better be true that I get 1. Otherwise, I don't have a total probability that adds up to 1, and the universe collapses into a hole or something. So, this is what we call our normalization condition. Normalization condition. We've discussed two types of probability, which is regular straight old probability, like you've talked about many times before, I'm sure, when you talk about flipping a coin or rolling a dice. We've talked about probability density, which can be used to find what's the probability of being between a and b if you have a continuous random variable. We're going to deal with one more type of probability distribution function. It's the cumulative probability distribution, which we define this way. The cumulative probability as a function of x is the integral from minus infinity to x of my probability density function, it's a function of x prime, dx prime. So let's put that into words. What's going on here? All we're doing is we're adding up a probability density function from minus infinity up to some value x. So what this means, I look at my some probability density plot. Suppose this is x. This is my p of x. This is my x. My cumulative probability is the probability that my random variable takes some value that's less than x. So it's just all of this probability, the area under the probability density curve. It's just all of that integrated up to the value x. That will give me the probability my random variable is less than the value x. To illustrate the differences between these different probability functions, let's do an example. So suppose I'm thinking of a real number between 0 and 10, and I am choosing those numbers at random. Well, we want to look at our probability density as a function of x, and we're going to go from 0 to 10. Now, let's suppose, for the sake of argument, that this probability density function is uniform, so that any number is equally likely. Well, that would mean that my probability density function looks like this. All values within the range from 0 to 10 are equally likely. What is that probability? What is the value of the probability density function that I choose here? Well, we could say, using our normalization condition, that 1 has to be the integral of p of x dx over the complete range. Now, in principle, I should say that this goes from minus infinity to infinity, but I know I have 0 probability of being below 0 and 0 probability of being above 10, so we're just going to go from 0 to 10. This is a constant value, so it's not actually a function of x. I can just pull it out, which would mean this is p times the integral dx from 0 to 10, or equivalently, we would say that 1 equals p times 10, so that we could say the probability density function is just given by 1/10. So I've normalized my probability density function by showing that it adds up to 1/10, and the value I get that makes that condition true is just 1/10. I've normalized my probability density function. Now let's compute the probability of having some values. So let's say I want to know what's the probability of having my random variable take on a value in the range 4 to 6. So I want to know what's the probability that x, my random variable, is between 4 and 6. Let's do that. We know that is just given by the integral of the probability density from 4 to 6, which is going to be the integral from 4 to 6 of 1/10 dx, which will be 1/10 x evaluated from 6 to 4, from 4 to 6, excuse me, will give me 6 minus 4. That'll give me 2, divided by 10 is going to give me a 1/5 probability. So I have a 1/5 probability of being between 4 and 6, which we can also see because the area under the curve between 4 and 6 is just going to be 1/5. We've normalized our probability density. We've computed the probability, in this case, of our random variable taking a value between 4 and 6. Let us now compute our cumulative probability function. So I want to find p as a function of x. This time p is our cumulative probability function, which we know would go from minus infinity to x, but in this case, since our probability density is 0 for any negative value, we'll just take it from 0 to x, p of x dx. And when we plug in, that'll be the integral from 0 to x, we should be primed, of 1/10 dx prime. So that will be 1/10 times x prime evaluated from 0 to x, which will give me x over 10. So if I were to plot my cumulative probability function, it would look like this. It's a function of x. It would just be, in this case, it would be a straight line with slope 10. That goes from 0 to a total probability of 1. Okay, so remember, the cumulative probability is what's the probability that this value, that this function, excuse me, that this random variable takes a value that is less than x. And if x is 5, what's the probability that I'm choosing a number that's less than 5? Well, it would be 1/2. What's the probability that I'm choosing a number less than 10? Well, it would be 1. So it's just what's the probability that my random variable takes on a value that's less than x. And if that's the case, we can tell that it always has to be, the cumulative probability must always be a monotonically increasing function. Because if I were to go down, if the function were to go down, that would mean that my probability, I've lost probability somehow. So since I'm just counting how much probability do I have so far, it's always going to be a steady increasing function of x. A particularly useful statistic that we're going to want to pay attention to is the mean, or average. So suppose I have taken a bunch of measurements of some quantity, and I get the following values: 1, 1, 1, 2, 2, 3, 3. What's the average or mean of these quantities? We're going to denote the average using these angle brackets. So if my random variable is x, we're going to say the average or mean of x is just going to be given by angle brackets. Sometimes we will also write the average as x bar, where the bar is just a bar over the variable. But to take the average, all we're going to do is we're going to sum up the individual outcomes of the measurements divided by the number of possibilities. Or the number of measurements. So in this case, we would say that the average of x is equal to 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 3. Divided by 1, 2, 3, 4, 5, 6, 7 measurements. 1, 2, 3, 4, 5, 6, 7, 10, 13. So that is 13 sevenths for my average value. There's another way that I can compute the means or averages of a distribution of numbers like this. What I can do first is compute the probability of getting any individual outcome. So here I've had 3 possible outcomes. I could have gotten 1, 2, or 3. And I can compute the probability of getting any one of those outcomes. So I have 7 total measurements. 3 of those measurements took on a value of 1, so the probability of getting a 1 is 3/7. The probability of getting a 2 is 2 out of 7. The probability of getting a 3 is also 2 out of 7. If I want to compute the mean from those probabilities, we can use this formula, that the average value of x is equal to the sum of all possibilities. Give myself a little more room here. The sum of all possibilities times the ith possibility times the probability of that possibility. So, if I were to write that out, that would be 1 times the probability of 1, which is 3/7, plus 2, my second possibility, times the probability of getting a 2, which is 2/7, plus 3, 3, times the possibility of getting a 3, that's 2/7 as well. So it's just the outcome times the probability of getting that outcome. 3/7 plus 4/7 plus 6/7 should give me 3, 4, 6. 3, 4, 6 should give me 13/7, which is exactly the number that we got before by computing the average directly just by taking the sum of each of the outcomes divided by the number of measurements that we took. So we can use this formula to compute the mean or average of a distribution of numbers. We've shown that you can compute the average value of some random variable by taking the possible values you can get, the possible outcomes that you can get, times that probability, the probability of getting an individual outcome. So for example, we took the outcome 1 and multiplied by the probability of getting a 1, plus the outcome 2 times the probability of getting a 2, etc., etc. Summed those all up, we got the average that way. But that supposes that you have a discrete distribution of random variables. What if you have a continuous distribution of random variables? So you have a continuous random variable. Well, the outcome will look very similar, but I don't have these probabilities here. I need to deal with probability densities. So instead of summing up probabilities, we're going to work with probability densities, which means we have to do an integral. But other than that, it looks exactly the same. It's going to be the probability of getting some continuous value x times p of x dx. So before, if I wanted the probability, I integrated p of x dx. Now the only thing I do is I include the value of the thing that I want the average of, and I integrate over the full range, minus infinity to infinity, or some other range if your function is only defined for certain values. Now, interestingly, this works not just for values of x, but for any function of x. So if I want to take the average of not x, but x squared or x cubed or sine of x, or any function of x, I would just put that function of x here, and I would get the average value for that function of x. I'm going to put a big box around this because that's important. You're going to want to write this down in your notes along with this one. Okay, so we can compute the average value for any function of x. Similarly, I can also do that here. I have a discrete number of measurements for some function I. Probability of getting I is just given. I can compute the average for any function of that random variable. To help see how we can compute averages, let's try doing a simple example. In this case, we're going to consider radioactive decay. So, the probability density that a radioactive atom is going to decay is given as a function of time by 1 over tau, e to the minus t over tau for t greater than 0, and 0 for t less than 0. So we're only starting our clock at time equals 0, where tau is just some decay constant. So let's see if we can figure out how this probability distribution works. We're going to try to compute a few different things with this. First of all, let me just leave this here so I remember what that function looks like. First of all, let's see if this function is normalized. So if I add up the total probability from this probability density, do I get 1? I better. It must be true that this equals 1, but we want to check that. Does this equal the integral of p of t dt over the complete range So from 0 to infinity, because remember we're not counting anything before time 0, well that'll equal the integral from 0 to infinity, 1 over tau, e to the minus t over tau, dt, which will equal the integral of e to the x is e to the x. I've got to take into account that there's a minus 1 over tau in that integral. So I'll get the integral from 0 to infinity, 1 over tau, minus tau, e to the minus t over tau. Oops, nope, I don't want that integral there. Sorry. Equals 1 over tau, minus tau, e to the minus t over tau, evaluated from 0 to infinity. I can tell this is correct because if I just take the derivative, I get a minus tau, and then that cancels the minus tau that I've brought down. These taus will cancel. So we will get minus e to the minus t over tau, evaluated from 0 to infinity, which will give me, at infinity, that will give me 0, because e to the minus infinity is 0, minus, at 0, that will give me minus e to the minus 0, which will give me minus 1, which indeed gives me plus 1 for my probability, as it must, because I need a normalized distribution in order to compute the probability correctly. So regardless what decay constant I choose, regardless what value I put in for tau, this probability distribution for the random variable t is normalized. Next, let's see if we can compute the average. So let's see, I want to compute the average of the random variable t, which will be given by integral 0 to infinity, probability of t, dt. So to compute the average value of t, that'll be equal to the integral 0 to infinity of, oops, sorry, I need to put my t in there in order to compute the average, otherwise I'm just doing my normalization interval again. So that'll be the integral 0 to infinity, p of t, which is 1 over tau, e to the minus t over tau, dt. So we'll need to do this integral. We could do the integration by parts. Alternatively, you could plug it into Mathematica. I cheated, I just plugged it into Mathematica. At which point you get e to the minus t over tau times t plus tau. It's not that hard of an integral to do, but it's more than I really want to spend the time doing right now. We have to evaluate from 0 to infinity. And when we do that, we will get, let's say, evaluating this from 0 to infinity. At infinity, e to the minus infinity is going to be 0. So we're going to get 0 for our first term, minus, actually there is a minus in front here, minus whole thing evaluated at 0. So that'll give me, e to the 0 will be 1. T at 0, that'll be 0. Tau will just be tau. So that'll be minus tau, which will just give me tau. So the mean of this probability distribution is just tau, that decay constant. We call that the decay time. So if the average time for radioactive decay is 10 minutes, that tau would be 10 minutes. Finally, let's compute the cumulative probability for this radioactive decay probability density. We do that, we get our cumulative probability by taking the integral 0 to t, p of t dt, and I should put primes on these t's in the integral to differentiate them from the limit t. So we do that. Again, this is an integral you can just plug into Mathematica. I'm not going to waste your time doing it here. You'll get 1 minus e to the minus t over tau. And if we were to plot that cumulative probability, you would get a function that looks like this. So remember, the cumulative probability is what's the probability that I have, that my random variable is less than a certain value. So for example, in this example, what is the probability that my radioactive atom has decayed by this time? So at 0 seconds, we would expect that there is no probability that it has decayed yet. And we would expect that over time, you get closer and closer and closer to a probability of 1. And indeed, if you plot this function, you will find that exponentially, this approaches 1. So it's 1 minus some number. But the number that you're subtracting decays exponentially. So it's just like exponential decay all the way up to a probability of 1. In addition to the mean, we have two other useful metrics for statistics. Those are the variance and the standard deviation. So suppose we have two probability densities. One probability density looks like this. One probability density looks like this. Which of those two results is more precise? Well, if I look here, this one would seem to be very precise. The vast majority of the probability has me lying between two values that are very, very closely spaced. So most of my probability lies between A and B here. Not so for this probability function, where my A and B are much further apart. They're more spread, they're more varied. This is a more precise result because my bounds are pretty close. Variance and standard deviation give me a method of measuring how tight those bounds are. To do that, we are going to compute a few different averages. We are going to define our variance as being the average of x minus the average of x. Whole thing squared. Now let's think about what that means for just a sec. I want to know how spread my values for the random variable are. So I want to know if this value is the mean. Remember, x bar just means mean. If that's the mean, how far away from that mean can I get? And I have two options. I can be bigger than the mean, or I can be smaller than the mean. Either of those options gets me away from the mean. So what I really want to do is I want to take an average of how far away I am from the mean. Well, let's go back to our function here. Let's rewrite it a little bit more slowly. I want to take an average of how far away I am from the mean. How far away am I from the mean? Well, that's my mean. That's where my random variable actually is. This is how far away I am from the mean. Now the problem is, I am going to be above my mean. I'm going to have a bigger value for my random variable than the mean, just as often as I am going to have a value that's smaller than the mean. So on average, if I average x minus the mean of x, I am going to get 0, because sometimes I'll be bigger than the mean, sometimes I'll be smaller than the mean. Since I don't want to just average positive numbers, what I'll do is I will take x minus the average of x squared, and then I'm going to average what that is. This is my variance. What it tells me is it gives me a nice metric for how far away my numbers, how far away my random variable can be from the mean. We can write that a different way. Let's actually do FOIL on this. So this will be the average of x squared minus 2x average x plus average of x squared, taking the average of that. So I'm taking the average of x squared minus 2 times x, taking x squared minus 2 times x times the average of x plus the average of x squared, and I'm taking the average of that whole thing. So that'll give me the average of x squared minus 2 times the average of x times the average of x. So that's the average of x squared plus, here's the average of x again. Remember the angled brackets and the bar are just the same thing. Average of x squared. So that'll be the average of x squared minus the average of x squared. 2 average of x squared plus the average of x squared. Now, you may be looking at this and saying, well, isn't this the same as that? No. The reason it's not the same is because I have to work in a particular order here. Do I square it first, or do I take the average first? Here, I take x squared, and then I average x squared. Here, I compute x, and I average all the x's, and then I square those averages. I flipped the order. Here I took the square first, there I took the average first. In general, those things will not be equal. So, is there an easy way to see that the average of x squared is different than the average of x, whole thing, squared? Well, suppose I only had 2 values for x, plus 1 and minus 1, equally likely. Well, x squared would be either plus 1 squared or minus 1 squared, and in both cases I'd get 1. So the average of x squared would be 1. However, the average of x would be the average of plus 1 and minus 1. The average of plus 1 and minus 1 is 0, which when I square that I get 0. So if you just take a simple case of 2 possible outcomes, plus 1 and minus 1, you get different values here. So we can see that the average of x squared, take x squared first, then average it, is not the same thing as taking the average of x and then squaring it. We will define this as our variance. Tells me roughly how far away I am, or roughly how spread out or varied my probability density is. And since it's a square number, a lot of times people don't like to deal with this as a square. They'd rather have something that has units of whatever the random variable is, rather than the random variable squared. So what we can do is we can define this quantity, which is the standard deviation, which is just the square root of that variance. Okay, so both standard deviation and variance tell us how spread out the probability density distribution is of my random variable. There are a couple of probability density functions that show up fairly often, so we want to pay attention to these in particular. One of these is the Gaussian, or normal distribution. It has a functional form that looks like this. P of x equals 1 over the square root 2 pi sigma squared e to the minus x minus a squared, quantity squared, divided by 2 sigma squared. For this probability distribution, this probability density, the mean value is just given by a. The variance is given by sigma. So you get to choose what the mean and variance of this function is. If we plot it, you'll see it looks like this. This is known as a bell curve. The bell curve is one of the most common curves that you'll see in statistics. It just comes from the Gaussian distribution. And we can specify both the mean, so that I can shift this peak around back and forth, and the standard deviation. So I can make my variance small so that it's a very tight, sharp peak, or broad if I make the standard deviation very, very large. So we can specify the statistics of many, many problems using this Gaussian distribution.